We want artificial intelligence to absorb entire code bases, sprawling legal libraries, and endless historical archives in a single glance. But feed an AI a massive, continuous text, and it quickly develops a functional amnesia. By the time it reaches the final pages of a long document, it has already forgotten the beginning. This happens because of a rigid hardware boundary known as the context window. It is a strict mathematical limit on exactly how many tokens, or words, a model can hold in its active memory at any given second. If an AI can only juggle a few pages at once, asking it to analyze a massive, interconnected dataset without a stable memory architecture is a computational impossibility. For years, engineers have bypassed this limit using a workaround called Retrieval-Augmented Generation, or RAG. Instead of reading a complete document, RAG shreds the text into small, isolated fragments and files them away in a vector database. When a user queries the system, it pulls only the few chunks that mathematically match the keywords in the prompt. The system only ever sees these disconnected pieces. Any overarching narrative, deep subtext, or complex logical connection spanning across the document is lost. Relying on this method to understand a dense text is like trying to comprehend a literary masterpiece by reading 12 random paragraphs taped to an index card. A different approach abandons vector databases and chunking entirely. It's called Cache-Augmented Generation, or CAG. Instead of breaking data apart, CAG feeds an entire unbroken document into the AI's key value cache in one continuous prefill pass. To test this architecture, engineers forced an AI running on a single A6000 GPU to ingest the entirety of War and Peace, all 922,000 tokens. This triggers a cold prefill. For 24.3 minutes, the GPU grinds continuously, loading every character and plot point into active memory. This 24-minute wait is a one-time architectural investment necessary to achieve total, unbroken context. The breakthrough happens next. The 23-gigabyte memory state compresses 5.75 times into a compact 4-gigabyte file. This cache is saved directly to the hard drive. Even if the server restarts, the memory state remains intact. When a user asks a question, the saved file is restored into the AI's active memory in just 1.2 seconds. With the complete text locked in, the model answers specific questions about the Battle of Borodino or character lineages at 100 tokens per second. By moving the heavy lifting to an initial ingestion phase, CAG makes massive document analysis feel instantaneous to the end user. There are practical boundaries to this system that keep it tied to specialized hardware. Running million-token CAG demands 24 gigabytes of VRAM. Without that overhead, you are forced to use a truncated context window or a smaller model. Pushing the AI's attention to these depths also exposes the lost-in-the-middle anomaly, where the model maintains sharp recall of the beginning and end of a document, but can occasionally drop details in the center. Despite these constraints, CAG removes the need to re-retrieve and re-embed data for every query, making it the more efficient choice for static, high-density archives. But there is a detail about this implementation and its 11-stage validation testing that stands out above the benchmarks. The code, the CUDA kernel debugging, and the GPU validation were all handled by an autonomous AI agent named Neo. An artificial intelligence successfully mapped out and optimized the exact physical architecture required to expand its own memory. We are moving away from searching through fragmented external databases and towards systems that treat massive datasets as a persistent, restorable state of the AI itself.